All right, this part here is 10.1 lecture video B. We're going to talk about deciding whether a given root is a rational, irrational, or not a real number. This here tells you about real numbers. Real numbers are a rational real number is a number that terminates or repeats, like 0.5. 1/2 is a rational number because it's 1/2 is 0.5. 2/3 is 0.66666. It just keeps on repeating. That is also rational. An irrational number is something like pi, where it's 3.14 and it just keeps on going. It doesn't stop forever. It just keeps on going and it does not repeat or terminate. The number 6 is considered to be rational because it stops. It's just 6. Something that is not a real number is known as an imaginary number. So let me just show you, just to make sure you guys remember. Remember, the square root of -1 is equal to I, and I squared is equal to -1, just to kind of refresh your memory on that from before. So please read the little chart and let's get moving to some problems. First of all, tell whether each square root is either rational, irrational, or not a real number. So on this one here, I have the square root of 27. Well, first of all, whatever's under the radicals can be multiplied together, and whatever's outside the radicals can be multiplied together. In order to simplify this, what we're going to do is, I know that the square root of 9 times the square root of 3 is the square root of 27. I can square root 9, and the square root of 9 is 3. Once you square root it, you're done. It's just 3. And I'm left with the square root of 3. Now, I know that the square root of 3 is actually an irrational number because it just keeps on going. It doesn't terminate or repeat. So when I take that number and I multiply it by 3, I'm going to get an irrational number. It's just going to keep on going forever. So this one here would be considered an irrational number. Okay. The next one, the square root of 36. The square root of 36 is 6. It is just plain old 6. It terminates. This is a rational number. Now, the square root of -16. That is actually not a real number. And because it's not a real number, I can break it up as the square root of 16 times the square root of -1. Because we know that from Algebra 2, you guys were all taught that the square root of -1 is equal to I, and I squared is equal to -1. That is just something that you guys learned way back in the day. If you forgot, there you go. So the square root of 16 is 4, and the square root of -1 is I. So the answer to this problem would be 4i. Normally, if this was Algebra 1 and we said the square root of -16, if there's a negative under the radical, we used to tell you in Algebra 1 that you can't do the radical. It would be like, okay, move on, go to the next problem. However, in Algebra 2, you guys learned about imaginary numbers. All right, let's go to the next one. This time we're going to find cube roots, fourth roots, and other roots. In 10.1 at the beginning of video A, I gave you perfect square roots, perfect square roots, perfect cube roots, perfect fourth roots, and perfect fifth roots. Those are things you have to memorize for the ACT exam. And here we go. So we went over this before. Please read this on your own. But let's look at finding each cube root. So in that list that I gave you, the cube root of 64 is 4. What that means is 4 times 4 is 16. 16 times 4 is 64. So another way to write it is the cube root of 4 cubed. Now remember, if you're taking the cube root of something that is cubed, whatever's being cubed comes out. So this is going to be 4. Now let's just say I want to be difficult. I can also rewrite this as this. You all believe that the number 4 can also be written as 2 cubed. Oops, 2 squared. I lied. 2 squared, everybody. 2 times 2 is 4. So in reality, this is just 4 raised to the third power. Once again, whatever's being cubed, when you have a cube root, whatever's being cubed, it comes out. So inside this parentheses, I have a 2 squared, and 2 squared is 4. Okay? So whenever you're taking a cube root, you want that to be a cube here. So these are just ways that you could do the problem if you did not memorize the cube root of 64 as being 4. Same thing with the cube root of negative 27. I know that my answer is negative 3. But if you did not know that, the cube root of negative 27 can be written as the cube root of negative 3 cubed. Because negative 3 times negative 3 is 9. 9 times negative 3 is a negative 27. So once again, if you're taking the cube root of something that is cubed, whatever's being cubed comes out. Hopefully you'll memorize that though. All right, the cube root of 512. You guys, I really don't know what that's going to be, so I'm just going to try this. I'm going to try 8 times something. I'm going to just try 8. So I'm going to take my calculator, and 512 divided by 8 gives me 64. I'm going to take this one. I know that's going to be 8 and 8. Remember, I need 3 numbers that are exactly the same. And I really didn't know. I just thought I'd try 8. So there's one, there's another one, and there's another one. So I could actually write this as the cube root of 8 cubed. And that would give me 3, 2, whoops, I'm so sorry. I need to do that one. The cube root of 8 cubed is just 8. So the cube root of 512 is just 8. Now, what if I wanted to write it out like this? The cube root of 512 could also be written as the cube root of 8 cubed. It could also be written as this. You all believe that 2 to the third power is also 8. So this right here is just 8 to the third power. So the cube root of, whoops. So what I could do is this. This is equal to 2 to the third power. 2 times 2 is 4. 4 times 2 is 8. I still get 8. The cube root of 8 cubed is also 8. The cube root of 512 is 8. So those are just different ways I could write this out if I wanted to. All right, just some different ways. All right, next one. Let's do the fourth root. The fourth root means you have to have 4 of the same number. So if you did not memorize this as 3, you could do the problem like this. 81, we know it's 9 times 9, but that's just 9 squared. I need 4 of the numbers. So this is going to be 3 times 3, and this is going to be 3 times 3. So I know that I have 4 3s. So the fourth root of 3 to the fourth power is 3. If you're going to take the fourth root of something that is to the fourth power, whatever's to the fourth power comes out. That's why the 3 comes out. All right? So that's one way of doing the problem if you wanted to. You can write it out like this. But if you memorize the fourth roots up to 4, you'd be good to go. Now on this one has the negative on the outside. Now the negative on the outside, and then we have the square root of 81. So I get negative, and the square root of 81 is, sorry, that's the fourth root, my bad. Fourth root. We already did this one. The fourth root of 81 is just 3. Whoops. So 3 times a negative is just negative 3. Okay? Remember, the negative on this one was on the outside. Now, on this problem, we have the fourth root of negative 1 times the fourth root of 81. Now, you can convert the fourth root of negative 1. And you can say that that is actually equal to I. You can actually do the whole math behind it. It's I, though. And then the fourth root of 81 is 3. So your answer would be 3I. Okay. Later on, I will show you how this converts to I, but I don't want to go through it at the moment because it's a lot of work. However, it is basically when you have a fourth root of something like this, we don't see that there is an exponent on here. There's actually an exponent of 1. We can actually write this as -1 to the 1/4 power. So if I have -1 to the 1/4 power, I can rewrite it as -1 to the 1/2 power times -1 to the, what was it again? -1/4 power. And when I did this math, remember when you multiply powers, you add the exponents. So when I add 1/2 plus a -1/4, I actually get 1/4. So what I can do is this. I end up with, this just means that it's a square root. So the square root of -1, I comes out. If I have something like this, the fourth root of -1 to the -1st power, because you have a negative exponent, you've got to flip it. So that's going to give you the fourth root of 1/1, which is just 1. And the fourth root of 1 is just 1. I told you this is a lot of work. But basically, the fourth root of the square root of, the fourth root of -1, it's just I. No big deal. And I proved it over here. All right. Hopefully I did it right. And then over here, we have the fifth root of 243. Now, I know that the fifth root of 32 is, no, that's not. Fifth root of 64 is 2. So on this one, I don't really know what it is. So we got to find it. We just know that there's got to be a number 5 times itself to give you 243. So I'm going to do some math over here. I have 243. And I'm looking at it and I could tell you that 3 goes into them. And the reason why I know that 3 goes into them is because I know 3 can go into 24 and I know 3 can go into 1. So that's going to be 81. And then this one here is going to be 9 and 9. And this here is 3 and 3. And this here is 3 and 3. So I have 1, 2, 3, 4, and 5. So that means I have 3 to the 5th power. Wow, that was nice. So I end up with the fifth root of 3 to the 5th power. Remember, the fifth root of anything to the 5th power means whatever's being raised to the 5th power comes out. So the answer is going to be 3. By the way, the ACT, I've never seen them make you memorize what the 5th power of 243 is. Okay? All right. So they do make you memorize the fifth root of 32 because that is 2. All right, that's about as high as it goes. Now on this problem here, because it's an odd number, I can write this out as -3 to the 5th power. Because a -3 times a -3 is 9. 9 times a -3 is a -27. A -27 times a -3 is 81. 81 times a -3 is -243. So I know that -3 to the 5th power is a -243 without having to do any of the work. Now, when you take the fifth root of something to the 5th power, whatever's being raised to the 5th power comes out. So that's going to be -3. All righty? And we did all the math over here. So that is that portion. Now we're going to talk about graphs. Graph function defined by radical expressions. These ones here are kind of nice because all we're doing is we are plug and chugging. First of all, a radical expression is an algebraic expression that contains radicals. It's the square root function. So if I have f of x equals the square root of x, what's going to happen is you're going to put in a value for x, which is what's under the radical. And then you're going to take the square root of it. Okay, the domain is all your x values. The range is all your y values. And when you have a square root function and you are taking the square root of it, I'm going to plug in, like if I plugged in the square root of 1, x is 1. Well, the square root of 1 is just 1. So it would have been 1, 1. So I would go over 1, up 1. If I put in the square root of 4, and if you notice, we didn't use 2 and we didn't use 3 for x because I don't really know what the square root of 2 is, and I don't know what the square root of 3 is. I would have to use a calculator, and we're not really worried about that. So if you notice, I used numbers that would give me a perfect square root. So we used the square root of 4. So when I take the square root of 4, I get 2. So I go over 4 and I go up 2. Now I use 9. The square root of 9 is 3. So I go over 9 and I go up 3. The next one I would use is the square root of 16, and that would give you 4. So if you notice my graph here, my domain is everything bigger than x, anything bigger than 0. My range is anything bigger than 0. So the way it has a bar here, that means it's included. The infinity means it's going towards the positive infinity. So it's going to the positive infinity, and it has a parenthesis, meaning that it goes on forever. Okay, let me see how many more I have to go through. I have a lot, so I'll do just a couple more, and then we're going to break it off here, and we'll go to the next graph, or the next video. All right, so now let's look at this graph. This graph is a cube root function. So for a cube root function, these are the domains. The domain means it goes forever on the negative side, and forever, x values can be forever on the negative side and forever on the positive side. And that is the x value. It starts here at the origin and it goes directly all the way over here, and same thing here. Now for the range though, for the range, eventually, this is the positive y-axis, this is the negative y-axis. As this thing grows, it goes on forever in this direction, and it increases a tiny bit each time. Same thing here. So my domain is anywhere to the negative x-axis and anywhere to the positive x-axis. That's why it's negative infinity to positive infinity. Same thing with range. Range means it goes to negative infinity all the way down here eventually, and all the way up there eventually. So that's what a domain and the range would be. The domain is your x-axis, your range is your y-axis. Okay,